All right, so today we'll look at conservation of matter. We saw conservation of mass. When we talked about mass, it would be something like this. If I had nitrogen plus oxygen, say combined together to form NO2, if I had 7 grams of nitrogen and it combined completely with 3 grams of oxygen gas, then I should end up with, if they all combine fully, I need to account for all 10 grams of this product over here, nitrate, or nitrite. So in doing so, it's 7 grams plus 3 grams on one side. This side is called what? Reactants. Good. So this is our reactant side. And on the other side, the arrow means yields or produces. And then you end up with a product. Thank you. What you have on one side needs to equal the other side. Right? That was for the law of conservation of mass. It's just looking at the mass of each side. We're going to look at matter today. It's a little different. With the conservation of matter, it'll deal something like this. In bio, you probably learned, I think we talked about this before, this thing's massive, C6H12O6. What substance is that? Glucose. It could also be fructose or dextrose, but it's a simple sugar. In here I have 6 carbons, 12 hydrogens, and 6 oxygens. I combine it with oxygen, and in doing so, it produces what? And remember? Water and carbon dioxide. And you also get from it energy. You get energy from it. And that energy is used to take a substance called ADP, adenosine diphosphate, and add another phosphate to it to form a substance called ATP, which is adenosine triphosphate, and that is chemical energy in your body that your body can use. So you've seen this. Yep.
So the energy is
Right. The energy from the bonds of glucose will be the energy you use to put a phosphate on. It's called phosphorylation. You put a phosphate onto adenosine diphosphate, to make a triphosphate. And those are high energy bonds that your body can use for muscle movement, for remember active transport, those kinds of things. It takes energy to do those things, to maintain your body temperature. So anyway, you have this formula. This is called cellular respiration. Okay? It's done with oxygen, so it's aerobic respiration. The opposite would be, remember fermentation? Lactic acid, and you can make, or ethyl, was it alcohol or lactic acid? Okay. If you don't, sorry. Anyway, this does not follow the law for the conservation of matter. This states I have 6 carbon atoms, but on the other side, I'm only showing 1 carbon. You can't do that. You can't lose matter. You have to account for it. So what I'm going to do is I'm just going to rewrite it, okay, just so it's easier for me to work with. C612O plus O2 yields CO2 plus H2O. I'm not going to account for the energy. I only care about the atoms. I'm counting atoms. And right now, it's not working. And then I do not have the right number. I have 6 carbons, and over here I only have 1. What I cannot do is this. This is illegal. I can't just drop a 6 in there. Because if I drop a 6 in there, it's no longer carbon dioxide, it's something else. And in reality, carbon dioxide forms. Well, that's what we're getting to. You're like 1 sentence ahead of it. Thanks. No. But I can't do that, though. That's fine. So I can't do that. But what I can do instead, if I need 6 carbons, I must form 6 carbon dioxide molecules. Now my carbons are good. When I look at hydrogen, I have 12 hydrogens total on the reactant side. I need 12 on the product side over here. I have a 2 here. I need a 6 in front to get to 12. and then I go to my oxygens, and I'm going to tell you that this is one of the tricks I want you to do. You do the singletons, they call it last. Because sometimes it's hard, sometimes it's easier. This is one where it's not going to be difficult. How many oxygens do I have on my product side? Total oxygens. Not 3. 18. Let's look why. I have 6 CO2s. Each CO2 has 2 oxygens. 1 carbon, if it's not written, you just assume it's a 1. 1 carbon, 2 oxygens. This contributes 12 oxygens. 6 times, it's not shown, it's a 1. 6 times 1, there's 6 here. A total of 18 oxygens.